Thingy. All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. I guess we can just jump right into it because we were in the middle of examples last time. So let me share my screen here. Make sure I can see the chat. Boom, boom, boom. Okay, so this was the notes from last time. We started the topic of related rates. The idea is when two quantities are related, so are their rates related via implicit differentiation. We know that this is going to be one of the word problems we're faced with. We know that we are looking at such a word problem. If we are told about some related quantities, we're given the rates of some of them, but not all of them, and we're asked to find one of the rates. Once you notice that that is the question, these are the 6 steps you go through. You always go through these steps in this order. Fully explain what you should do in each step, why you should do it, and at the end of the day, with enough practice, you'll have that all internalized, and just by memorizing the bold letters, or even just the one-word letters, the one-word phrases, memorizing the bold phrases, or just the one-word phrases that I was using in working these out, you should be able to just remember the steps in this order, right? So by the time you get to a quiz or a test, you shouldn't be thinking, oh, what should I do next, right? Because you kind of already messed up if you're in that situation. Yeah, so those were the steps. Again, something that's very important is that t is always the independent variable. Always, okay? You're always doing this with respect to time. Another notable thing is that when you get to step 6, sometimes you don't have all the information. You should not panic in this situation. You could go back to step 4. Another important piece of information, remember all your geometry formulas. They will come in handy. As you can see, we looked at a bunch of examples where we were constructing triangles and all sorts of things. But we went through a bunch of examples, and in every one of those examples, you will notice that we went through the 6 steps. Read, diagram, what you know, what you want, equation, differentiate, plug in. Read, diagram, what you know, what you want, equation, differentiate, plug in, right? Read, diagram, what you know, what you want, equation, differentiate, plug in. Always the same thing over and over. This is how we solve all these problems. And I asked you guys to try these 3 for today's class. So we are going to begin by knocking these out. So this is what we wanted to try for today's class, which is the 14th. Do more related rates problems. And hopefully we have enough time to actually start the topic of max and min values. We definitely wouldn't finish it today. I could probably finish it in a full session, but since it's going to be a partial session, we will only just make a slight dent into it. So did you guys try this? What were your answers?
I got 72 inches squared per minute for the surface area, and then 24 inches cubed per minute.
Okay, so these are guesses. Okay, let's see how they pan out. The side length of a cube is increasing at a rate of 2 inches per minute. When the side length is 3 inches, A, how fast is the surface area changing? And B, how fast is the volume changing? Now, these are 2 different questions. So let's take them one at a time. A, how do we do it? 1, we read. So related rates problems, we have all the important information. 2, diagram. It's a cube, which means it's a box. With all sides equal, right? So this length here is, say, call it x, x, and x. Length, width, and height are x, right? So that is our guy. You will notice that this has So that's behind it, which is going to come in handy in the first part. So yeah, that is our diagram. So here, x equals side length. And what do we care about? A equals surface area, which you can't really see on the picture. That's a calculation that you have to do, right? So that's our diagram. Okay, cool. Moving on to 3. What do we know? What do we want? We know that the side length is changing at 2 inches per minute. So we know that dx dt is 2, specifically a positive 2. And what do we want? How fast is the surface area changing when the side length is 3? So we want dA dt when x equals 3. Moving on to 4, equation. This is a prism. Well, here, I was going to say the volume thing, but we're dealing with the surface area first. This thing has 6 sides, right? The front, the back, the left, the right, the top, the bottom. The area of all of them, they're all squares of length side x by x. And so we have x squared for each of 6 faces. Each face has area x squared, and there are 6 faces. Right. So we weren't told that, oh, there's no bottom or top or anything like that, which we'd have to read. Since we read carefully, we know that all 6 faces are in play. All right, so that's our equation. 5th thing that we are going to do is we're going to differentiate. Okay, what is the derivative of this equation? What would we get?
dA dt equals 12s dx dt.
Right, dA dt is equal to 12x dx dt. And then we move on to 6, plug in. So we know what x is and we know what dx dt is. So we have everything, right? This is the guy that we wanted. So this means that dA dt is going to be 12 times our x was 3 times our dx dt was 2. So that leads us to 12 times 3 is 36 times 2 is 72. And dA dt is 72. And this would be inch squared per minute. Although, like I said, I don't particularly care if you guys get the units or not. If this was a physics or a chemistry class, I would care, but I don't particularly care. Get the number 72. Like that's what you need to get. So yeah, that was 72. So the guess was correct. Let's move on to B. So B starts out very similar. It's the same object, right? So, I mean, we are going to be very similar up to like step 3. Let's use technology to our advantage here. Move this out the way, maybe down here. The differences in part B, we want to know, we care about the volume. So I would, instead of surface area, I'm now going to measure volume. And we have the same given information, except now we want something different. We want, how fast is the volume changing at this point? So we want dV dt when x equals 3. So now we're at step 4. We're going to come up with the equation. V equals x cubed, right? So prism, area of the base times the height, x times x times x, length times width times height. Hopefully you guys remember that. So you need to remember your 2D, your geometry formulas from high school. So that's our V. 5, we're going to differentiate. The differentiation is implicit with respect to t always. So this is dv dt equals 3x squared dx dt. We're going to get to the point where we plug in. So the dv dt is the guy we want. So we are going to have dv dt equals 3, x was 3, dx dt was 2. So we have that. So we have our dv dt is equal to 9 times 3. That's 27. Our x is 3 and dx dt is 2. dx dt is 2, x is 3. 9 times 3 is 27 times 2, 54. And this is inch cubed per minute. Did you say 54 or 24?
I said 24, yeah.
You said 24?
Yeah, I multiplied the 2 instead of the 3.
Oh, you had a 2 in here. Yeah.
Yeah, I squared 2.
Okay. So, I mean, that would be like a 1-point deduction or something. If you messed up, if you put a 2, you put a 2 right here, right? Yeah. Just be a little bit more careful. That's why we. All right. So 54. Now let's get this guy. Problem 8. Any guesses on this one? This one is actually like a tough one. Like, I think to set up. Well, if you don't know the trick, it's super tough to come up with it, I think. So let's just do it. Let's just jump in. Maybe I can magnify these things a little bit. Let's see. Yeah, there we go. So we have at noon, ship A is 80 miles west of ship B. At this time, both ships set sail. Say that 3 times fast. Ship A sails south. Say that 3 times fast. At a speed of 20 miles per hour. Ship B sails north at a speed of 10 miles per hour. How fast is the distance between the two ships changing at 2 p.m. if both ships maintain constant speed? So ship A and B set off. They're moving at a constant speed, and they move in the way described. So 1, of course, is to read. 2, that description might confuse you, which is totally understandable. So we need a diagram to figure out what the heck is going on here. All right, so what were we told? there were two ships, ship A and ship B. And A was 80 miles west of ship B. So there was a distance of 80 miles here. Okay, all right, so we have that. Ship A sails south. So A starts moving. A starts moving south. So, boom. Right, and here is where A at 2 p.m. Right, and B starts going north. So at some point we have B at 2 p.m. Okay. Now what we want to measure is the distance between them. Now, of course, in math, unless otherwise stated, when we say distance, we're talking about the straight line distance. So here is the distance, the length between them. Okay, that's the length that we want. Now, notice that the green lines and the red lines will change. So the farther they keep traveling, the longer the red line is going to get and the longer each of the green lines are going to get. So we should label these with variables. So let me label this with X. So X is the distance, or the distance A travels. That's X. And let me do Y for the distance V travels. So those are variables. And of course, the distance between them is going to change the farther they go. So I would also label that with something, say Z. This is the distance between A and B. Okay, so we kind of have this guy. You can notice that there are right angles here. So we kind of have a pair of right triangles, which is kind of annoying. I don't want to have to set up two formulas or anything like that. So there's a very clever trick that we can do here. Whenever you have two right triangles like this, you can actually create a much larger right triangle that can talk about both of them at once. And you can do that by just adding this part here. So what color do I want? So if I extend this vertical line down until it reaches the level of A, you'll notice that I would have created another right triangle, a very big one. So now what I would say is, let's use the large right triangle for our diagram. So essentially now we have a right triangle that looks like this. The length of the base is 80. That's not changing because the A and B are moving vertically. So how do I label it when it's not changing? With a constant. It is 80. All right. Now this length here, we already called it Z. And what is the big length? What is the vertical height? What is the height of this?
60.
The height of what? What part? I'm talking about this length here. What is that?
And isn't it like x plus y?
It's X plus Y. right? You can't label it with a number because it's changing. It's in fact, it's growing. So that is our diagram and proper labeling. Yeah. So now move on to step 3. What do we know? And what do we want? We know that how fast X is moving, which is A, right? X corresponds to A. And that is 20. We also know how fast Y is changing. That is 10. Right. And we want to know how fast the distance between them is changing when clock shows 2 p.m. Now we have to kind of understand what that means in terms of our variables. How would we know? What does it mean for the what happens at 2 p.m.? So at 2 p.m., can you tell me about X and Y at 2 p.m.? What would X be at 2 p.m.? So they start at noon. A is traveling south at 20 miles per hour. At 2 p.m., what is X? Anyone? Bueller? 20 miles per hour, meaning every hour you cover a distance of 20 miles. We start at noon and we're measuring at 2 p.m., which means 2 hours has elapsed. What is the distance that we've traveled?
40.
40, right? So here, X would be 40. What about Y? 10 miles per hour. And we've been traveling for 2 hours. So it's 10 times 2. There's this viral YouTube video about this guy making fun of his girlfriend. I think there are a bunch of them now since then, but the most famous one I know of is that one where he's like, okay, if we're traveling 80 miles per hour, how long is it going to take to travel 80 miles? And she couldn't figure it out. This is why understanding units is important. Yeah, 80 miles per hour means you take an hour to travel 80 miles. That's what it means. Miles per hour. So how many distance covered in an hour? So yeah, so that is what we want. Moving on to 4. We need an equation now. Here's our diagram. What equation can you come up with that relates all those variables?
Z squared equals 80 squared plus X plus Y squared.
Yep. So we have Pythagoras' theorem by Pythagoras. We know that Z squared is equal to 80 squared plus X plus Y squared. So that's our equation. And 5, we're going to differentiate this equation. We're going to differentiate it with respect to t, always with respect to t. So here we're going to have 2z dz dt equals derivative of 80 is squared is 0 because 80 is a constant. And then chain rule here, 2x plus y times the derivative of the inside, which is dx dt plus dy dt. Of course, we could cancel the 2's here, divide both sides by 2. So this would mean that, what do we actually want here? dz dt. So this is the guy we want. This actually means that dz dt is equal to x plus y times dx dt plus dy dt for z. So now we move on to step 6. We're going to plug in. All right. So we know that dz dt is equal to, I know what my x is and my y is. X was 40, y was 20. X was moving at 20 miles per hour, y was moving at 10 miles per hour. And we're dividing by z, the distance between them. And we were told that was, geez, we weren't told, were we? We have a z here. Is it time to panic? No, it's not time to panic. Go to step 4. We know that z squared is equal to 80 squared plus x plus y squared. And we want x equals 40, y equals 20. So this means that your z squared is equal to 80 squared plus 40 plus 20 squared. That's 80 squared plus 60 squared. What you can notice so you could square 80, square 60, add them together, take the square root, or you can notice that 80 is actually 4 times 20, and 60 is actually 3 times 20. Okay, so that's a right triangle where the sides of the legs are multiples of 4 and 3. It means that the z must be the same multiple of 5. By 3, 4, 5 triangle. And so this means that your z is 100. Now you go back to step 6. And we can plug in. We had 40 plus 20, 20 plus 10. Over 100. So that was 60 times 30 over 100. These guys cancel. So we just have 6 times 3, 18. So it's moving at 18 miles per hour. Okay. But that one was a tough one. Coming up with the diagram would probably be the hardest part here. But now, once you've seen this trick, it'll be easier for you to see it in the future, right? Sort of other tricks that you want to remember from geometry are things like, so, constructing a big triangle to encompass 2 triangles. Another thing that might come in handy is just using similar triangles, right? When one triangle is inside of another one, which you get by slicing parallel to one of those sides, then the smaller triangle is actually proportional to the bigger one. So that's similar. That's the concept of similar triangles. So now let's let's do this problem, which is all right. Problem 10. Superman is cruising at 390 feet per second. He's at an altitude of 5,000 and he flies directly over Jhevon's house. He always does this every Sunday. Assuming Superman maintains this altitude, right? He maintains altitude and speed, so that's not changing. How fast is the distance from the house of Superman changing at the time when Superman is 13,000 feet from the house? So one, read. It's a related rates problem. Two, I need a diagram. So what would this diagram look like? Well, here's the ground. Suppose this dot here is Jhevon's house. Okay. And Superman is flying overhead. So Superman is going like so this is Superman's trajectory. Okay, so this is at a height of 5,000. And so suppose Superman is right here. Okay, so the distance between Superman and my house is going to be this red line here. Right, so this is now notice that that is changing. To make this a little bit more usable, what I could do is I could measure the altitude right above my house, right? So this is length 5,000. And what I just did was I created a right triangle, in which case this distance here is also changing. So this is the distance Superman traveled since passing over the house. It's also changing. The altitude is not changing. We are assuming that he's maintaining altitude and speed. So this leads to my diagram is like this upside down right triangle, where this side is always 5,000. This side can call it X. This side can call it Y. So that's our diagram. 3, what do we know? What do we want? We know how fast Superman is flying, 390 feet per second. That is just actually how fast the x is changing, specifically increasing. So we know that dx dt is 390. Positive, because he's and what else is changing? The y. But we want to know how fast is the distance from the house to Superman changing. So that's what we don't know. So dy dt is what we want. When do we want it? Now. No, we want it in a specific situation. We want it when Superman is 13,000 feet from the house. So the distance from the house is y. So this is when y is 13,000. Moving on to 4, we're going to set up an equation. What equation can we use here? Equation?
Y squared equals x squared plus 5,000 squared.
Yeah, again, by Pythagoras. It's a common thing. If it's a right triangle, chances are you're going to use Pythagoras because of all the lengths. If I ask about the area, then yeah, you'd use half base times height. But you're not going to use trig, so you're never going to need to know, oh, sine is opposite over hypotenuse. So Pythagoras or like the area formula is the only thing you need to know for a triangle, I guess. By Pythagoras. We know that y squared is equal to 5,000 squared plus x squared. And 5, we're going to differentiate. So we're going to have 2y dy dt equals 2x dx dt. I could divide both sides by 2. And so I get that my dy dt is equal to x dx dt over y. So I'm going to move to part 6 where I'm going to plug in. So I have my dy dt. That's in fact the guy I want. It's going to be equal to x. Don't think we were told x. We were told how fast x is changing. And we're told that y is 13,000. X, we don't know. So go to step 4. We know that y squared is equal to 5,000 squared plus x squared. And we know that y squared, we know that y is 13,000. In other words, what you're going to realize is that this is 13 times 1,000. This is 5 times 1,000. And so x must be this is another special triangle. I did mention it yesterday. It's going to be something times 1,000. What was the special triangle here? So, yeah,
12.
Claudia?
Yes.
12, right? So there's a 5, 12, 13 triangle, right? Those go together. 5 squared is 25, 12 squared is 144. You add 25 to 144, you get 169. 169 happens to be 13 squared. So those guys always go together. At 12. 5, 12, 13 is another common pairing. So 3, 4, 5 and 5, 12, 13 are pretty much the most famous ones. 3, 4, 5 especially. So you definitely, if you're trying to find side lengths of a right triangle, unless the numbers are super small, chances are I'm going to hide a 3, 4, 5 triangle or a 5, 12, 13 triangle in there because I know you guys aren't supposed to use calculators. So I'm going to give you numbers where there are tricks for you to be able to do it by hand. So yeah, so this means that our X is actually 12,000. And with that, we can go back to step 6. So we had that our dy dt is going to be equal to X, which is 12,390 over 13,000. Was it 390? Let me make sure. 390 feet per second. Yeah. So of course you could cancel all the thousands. 13 does go into 39 3 times. So that goes into that 30. Yeah, and so we have essentially 12 times 30. So that's going to be 360. Feet per second. That's that one. All right, so these are some more challenging problems. So like these last two, like this one and that one, these are like final exam type problems, right? Whereas the others, like I could give you these on a quiz and it wouldn't, right? All the other examples I did kind of like quiz stuff. I would, again, highly recommend you practice a lot of these. So in the last lecture, I gave you a lot more examples than we did. So you can try problems 2, 6, 7, 9, 11. See how far you can get with those. I'd also recommend, of course, there's going to be more in your homework. Did I post homework for related rates? I don't know. I will. I will soon. I'll post all the chapter 4 homework because we're going to be doing chapter 4. And practice a lot. Getting through problems like this should become almost second nature. You might have slight hiccups during step 2 when you're trying to figure out what's going on and drawing diagrams. But other than that, you should be able to get through a related rates problem in relatively short order. Yeah, that's all I wanted to do with related rates. Let me just give you some definitions for what we're going to do next time. So next we have 4.2 max and min values. Right. Short for maximum and minimum values. Right. Okay, and we're going to just jump straight into some definitions here. Let f of x be a function of x. Let I be some interval on the real line, interval on the number line. So now let's look at some definitions. We say f of x has a or an absolute or global maximum at x naught on I. Let me say it the other way. On I at x naught if f evaluated at that point gives you a larger output than all other things on that interval. Okay. So something has an absolute or a global maximum if it's a point where the output is bigger than everyone on the interval that you're looking at. Definition. Similarly, f of x has an absolute or global minimum on I at x naught if it's smaller than everyone. Okay, so this is an absolute or a global minimum. On a global scale or an absolute scale, any point where you're larger than everybody else, larger than or equal to everybody else, you're called an absolute maximum. Any point that is smaller than or equal to everybody else is called an absolute minimum. There are very similar ideas, but on a local scale, not a global scale. So these guys, you can actually on iPad. Okay, so absolute global minimum and maximum. You have something that's called also a local or relative maximum. And this is just for all x near x naught. Similarly here, we can have a local or relative minimum if it's smaller than or equal to, if its output is smaller than or equal to f of x, again, for all for x in I near x naught. And near is a vague term, which is just means for some open interval, very small. Again, sort of vague, but we'll get the intuition next class. Very small, centered at x naught. So you go to x naught, open up a small window, and then you check in that small little neighborhood, is this guy the biggest or the smallest? And if so, we call it a local max or min. That's pretty much it, but I want to tell you another name for these things. I want you to note max and min points are sometimes called extreme points. The plural of which is extrema. So you can have things phrased a different way. So if I say absolute extrema, it's the same thing as me saying to you absolute maximums and minimums, right? They mean the same thing. So you'll see in your textbook and homework, sometimes they're talking, oh, find the absolute extrema or find the global extrema. They're talking about the max and min points. Find the local extrema. They're talking about the max and min points. So instead of max and min, sometimes we call it extrema. And that is it. So for now, so those are some of the definitions. So absolute max or min, absolute max means you're bigger than or equal to everybody on the entire interval. Absolute min, you're smaller than or equal to everybody on the entire interval. We say you're local or relative if you're greater than or equal to just people close to you, people in your little neighborhood. And we use local min to say you're smaller than everyone in your little neighborhood. Not on a global scale, but if I just zoom into you, you're the biggest or the smallest guy there. And that's the difference between local and absolute. We'll do a little bit more intuition on these definitions next time and learn how to find these points. It's actually a very important thing that we're able to find them. So we'll stop there. Thank you for your time and attention. Hopefully you have the rest of a good rest of the day. I will see you guys all on Friday in the next one. Ciao.